The problem statement from GATE Physics 2012 reads as follows. Consider the following circuit in which the current gain beta DC of the transistor is 100. We have been given a circuit with NP and BJT with a few resistors, and the questions ask which one of the following correctly represents the load line, that is collector current IC with respect to collector emitter voltage VCE and Q point of this circuit. So what are these two things? We'll see in a little while. This is a multiple choice question with only one correct answer. Let's get a brief view into the working of an NP and BJT. On the top left here you have an unbiased NP and BJT, and if we bias it in this following manner, that NP is forward biased, base emitter is forward biased and base collector is reverse biased, you will get a large amount of electrons injected into the emitter. From the emitter to the base, a few will recombine, while the majority of them will get collected at the collector, and the currents will obviously be in the opposite direction of the flow of the current. And due to the application of bias, the Fermi levels shift accordingly, and you can see a large amount of electrons coming in, very few recombining, some holes also diffuse back, while the most of the electrons are collected. Mathematically, these can be represented as this first expression is nothing but the Kirchhoff's current law, IE equal to IC plus IB. Beta is the current gain, which is collector current over base current. Alpha is the collector current due to over the ammeter current. Alpha is usually very close to unity. Now I just told you that here in this diagram is base emitter is forward bias, so collector base is reverse bias. However, there are four such configurations, and the most commonly used when I told you base collector reverse, base emitter forward, is we called this at the active or the forward active region, and you see is this region between the points B and C. This is the forward active region. The other region is forward for when both the p-n junctions are forward bias, and this is called the saturation region. You can see in between the points A and B. Here the transistor is behaving more or less like a resistor, because you see I is right proportional to V here. A third region is when the base collector is forward by the base emitter is reverse. This is called the reverse active, which is not shown here. Essentially the emitter and collector have reversed their roles. And finally, when both the p-n junctions are reverse bias, and this is the cutoff region, which you can see here in this grayish region. We do not operate beyond VCE because that device tends to break down. So you can see after the point C, we do not usually operate. Now this is called the output characteristics. This is IC versus VCE, and you can see as we increase IB, IC increases, because we know that beta equal to IB upon IC. You know that beta equal to IC upon IB, so IC is nothing but beta IB, beta being a constant. As we increase the IB, IC should increase. Now the second concept that we should talk about here is the load line. So what is that? So I've drawn the circuit here. This is the RC that you see, collector resistor. This is the RB here, RE here. Let's assume a current IC is flowing here and IE is flowing here, and obviously a current IB is also flowing here. Right, so now what I'll do, I'll apply a KVL across the green line. So I can simply write that VCC minus ICRC minus VCE. Note that this is collector, this is emitter, so this drop is VCE, right, minus IERE equal to 0. Now note that we are assuming this is in forward active mode, so we can assume IC and beta is high enough so that IC is approximately equal to IE. So I'll replace IE with RC, and I'm keeping all the IC terms on the left. So I'll get IC as RC plus RE, which is equal to, so what I'll get is VCC minus VCE, right? And let's call this term RL. So I'll get ICRL equal to minus VCE plus VCC. And if I note that the y-axis here is IC, like this, so I am keeping y equal to mx plus c. I'm trying to, so y equal to x is nothing but VCE. Note this is the x-axis, so I'll write minus 1 by RL times VCE plus VCC over RL. Now if you see this last line, this expression, this is what's expression of a load line. Why we call it a load line? Because the term RL appears, it corresponds to the load, and this is a straight line. So if I want to plot it, it will look something like this. Why? Because you see when VC equal to 0, the current will be maximum then, which will VCC by RL, which is denoted here. However, when VCE when IC is 0, IC will be 0, then VCE will be VCC. So this is the region, this is the line that we get, and this is called the load line. Now this was the circuit diagram that was given to us. Beta was equal to 100, some denoted some node voltages, and what we required to find, we are required to find the Q point, which means we need to find IC and VCE. In order to do that, let's apply KVL across the green line. So I'll write that will be 15 minus 100k times IB minus VBE minus, that is 100 times IE equal to 0, right? So if I do this, I'll plot everything in terms of, let's say, IB. Okay, so let's keep that term here. So I can write 100k times IB plus 100 times IE is equal to 15 minus VBE. Now I'm assuming it's forward active mode, so VBE I can simply assume to be 0.7, and let's also assume that then in forward active mode IE will be beta plus 1 times IB. So let's put these values here. I'll take IB common. It will be 100k plus 100 times beta plus 1, which is equal to, that's 15 minus 0.7. So I'll get IB into, that will be 100k plus 100 times, that will be 101. So that will be 10.1k, which is equal to 14.3. So if I put this here, then this will come out to be 14.3. IB will come out to be 14.3 divided by 100.1k, right? And so simply know that IC is equal to beta IB, so that will be 100 times 14.3 over 110.1k. and if you go ahead and solve this, this will come out to be so this will be 13, so that will come out to be so that goes away completely, so this will come out to be around 13 milliamperes. So we have obtained that the collector current is nothing but 13 milliamperes. Now the next thing we need to find is nothing but VCE. So now we'll simply find VC. How do we find VC? So VC is nothing but, if we apply Ohm's law across this resistor, so I can write 15 minus VC equal to 900 times 13 milliamps. So this will give me VC equal to 15 minus 13, it's 11.7, so that will be 3.2 volts. And similarly, if I apply Ohm's law across this resistor, I can simply write that VE minus 0 is nothing but 100 times IE. IE is approximately equal to IC, so that will be 100 times this 13 milliamps, so that will be 1.3 volts. So this implies VCE approximately 3.2 minus 1.3, that's 1.9 volts, right? So we have obtained that VC that IC is 13 milliamps and VC is 1.9 volts. So let's go back to the question. We obtained that the Q point, note the Q point we obtained as 13 milliamps and approximately 1.9 volts. So 13 milliamps, option A, 13 milliamps and 2 volts. So Q point we have obtained. Now the second part was the load line. Now we told you the extremities of the load line, we just discussed that it's the x-intercept is nothing but the VCC. So VCC is 15 volts. So this is going to be 15 volts, which is true, which is VCC, and this point is nothing but VCC over RL. I told you IC max, right, for load line, and RL is nothing but 900 plus 100. So RL is nothing but 900 plus 100, which is equal to 1 kilo ohms. So if you put it, then IC max will come out to be, VCC is 15 by 1k, so that will come out to be 15 milliamps. So ICC max should be 15 milliamps, which is this point. So you can see 15 milliamps and 15 volts are the extremities, are the intercepts of this load line. So which again matches the option A, and we obtained the Q point was 2 volts and 13 milliamps. So option A matches both Q point as well as the load line. So that is our answer. Thank you for listening.